think back to the year 2001. And in that chat box, I'd like you to just type in a few things of what you think about of technology in 2001. Let's warm up your keyboards. And we have Mr. Feltner saying AOL. Oops, hold on a second. What happened to my chat box? Dave Mahalik says the flip phone. Wayne Hollett says no Facebook. Can you believe there's a time before Facebook? Blu-ray. The Nintendo 64. Playing Snake on your dad's Nokia cell phone. Some folks are giving their age on this. These are all excellent examples. Certainly Nokia was the hottest tech company. And of course, America Online was a multi-billion-dollar behemoth. This was also the time that in our RV industry, manufacturers starting to experiment with things like multiplexing. There was multiplex lighting systems just starting to be offered by a variety of different vendors. We were starting to get just a little more sophisticated, more complex things like automatic gen starts. The tank monitors were becoming more than just a couple little LEDs that you press a button and it ran on resistance. Engine monitors. We had some of the first electronic engines at that time, and we're starting to see some electronic instrumentation in the dash. So here we are in 2001 as an industry, and it was becoming apparent that this technology is coming and it's coming fast. And there was danger. There was danger for vendors. As vendors, the idea that every different manufacturer might have their own systems, and as vendors, we'd have to develop something special for Fleetwood that would be different than what we had for Monaco, that would be different than what we had for Country Coach. This was a real concern. Meanwhile, on the builder side, they had the twin danger that they wouldn't be able to get from the vendors what they needed, or they'd get locked in to specific products from specific vendors. And needless to say, from the technician's point of view, it was a potential nightmare, and from our customers, in which every different RV would have different systems, which would have different tools and techniques necessary to troubleshoot and fix them. So this was a very real set of problems coming on the horizon, and it is to the eternal credit of the RVIA and some of the visionaries within this organization that we took the bull by the horns and actually created a committee to deal with this. So the committee was created, and at that time got about 30 or more vendors in those early meetings, several of the OEMs. And the first question we had to ask as a industry, even in 2001, there was a lot of technologies out there, Ethernet, for example, and LawnWorks, J1708. There's a lot of technologies out there that other industries used. But, we realized right away that there's some things that are very unique about our industry. There are things that are special about the RV industry that we had to take into account in creating our own protocol. Again, head to the chat box there and think about what is special about the RV industry that we couldn't just pick up something from another industry and use it. What are the things that are unique, not necessarily unique, but special to our RV industry? An excellent one comes up right away. Long cable runs. RVs are big, at least some of them are. And the necessity to be able to connect everything in a 40-foot, 45-foot motorhome is pretty substantial. Tight spaces. Someone points out that you have both the coach and the chassis. It's one thing, there's a lot of home automation. Home automation was just starting to be a thing then. And it's one thing to automate the home. It's another thing to automate the car and put that all together into one. Be pointed out. Very good point. Someone points out they have some special things like holding tanks, which are kind of unique. We don't see that in homes. And to summarize that, someone says it points out it's a home on wheels. I'm a little bit surprised that nobody's come up with the thing that was probably the very first thing that was mentioned in the committee. We're cheap. We've got another saying that everything can be wired differently, and this is part of a broader question that we have. I notice also RF interference, an excellent point. Let me bring up, here are some things that I pulled from my memory from those early meetings as some of the most important items. So number one, in no particular order, is reliability. This thing has to work. It has to be able to work not just while it's in production and not while it's at the dealer's lot, but RVs last a long time, and it needs to be reliable for 20 years or more. One thing that was mentioned here, it has to work for a wide variety of products. We're doing everything from holding tanks and water pumps all the way up to very sophisticated generators and inverters. We need a system that is powerful enough that it can handle, say, a multiple inverter charging system and all the coordination that might take, but at the same time be cheap enough that we can put it into a water pump. Which better have lots of tools. This is one for most of the folks in this committee were engineers, and for all the actual development engineers in the group here, you know how important it is that there's tools out there to help you design your circuitry and write the software. And of course, the one I already mentioned and put it in italics here, it has to be cheap. It has to be inexpensive. It's one thing to design a protocol that we can put into $1 million bus conversion, but we need a protocol that we can also put into a inexpensive pop-up trailer. So those were the priorities, along with a lot of things that you've mentioned here, of that first committee. And we really spent a lot of time just looking at these core requirements and then looking for a protocol, a technology that would let us accomplish all this. That technology, by the way, is called CAN, Controller Area Network. It was designed by Bosch for anti-lock brakes. Bosch was the biggest brake manufacturer in the world. They created this protocol and put it out into the automotive industry to do anti-lock brakes. Anti-lock brakes, of course, is where the engine, transmission, and the brake system all coordinate so that instead of skidding and it will use the engine compression to reduce the speed, and the brakes interact with transmission and everything else. Obviously, anti-lock brakes has to be reliable. So also, CAN bus, it works for a wide variety of products. We say this because by 2001, virtually every processor family out there had a version that included CAN on it, CAN controllers on it. So whether you're dealing with a little 8-bit microcontroller for, say, a dimmer, there was a version of that processor that would have a CAN controller on it. But if you're also doing a 32-bit microprocessor for an advanced inverter charger, the same thing was true. It was easy to add for that, add to that processor. So it was a technology that we could apply to any kind of product. Lots of tools available. Again, since every processor family had that, there was lots of toolkits for it. Very popular protocol used in a lot of different industries. And as far as being cheap, today, you're looking at your largest expense being a transceiver and probably the extra pins on the microprocessor. To add CAN bus to a typical product can be $1 or $2 type bill of material expense. So CAN bus was a pretty natural choice for the committee. To be honest with you, there was almost there's barely any competition for it. Now, besides all, some additional traits we really like. So absolute requirements, but they sure turned out to be very handy for us. One of them is that CAN bus is inherently peer-to-peer. That is to say, master, there's no router or hub required. So there's no single point of failure for it, and no in particular router hub type technology. It works on very ordinary media. Your typical CAN wiring is using 18 gauge or 20 gauge wire. Work with ordinary wiring tools. The technician doesn't need anything special in his toolbox. And we'll talk about this one a little bit later. It strikes the right balance between being able to move lots of data and being able to respond immediately. CAN is capable of moving enough data for things like the inverter chargers to coordinate their activity, but it doesn't lose the responsiveness as a result. So let's move on now and let's look at the physical layer here. Monica? Okay, so I made just a very simple sort of schematic of what an RVC bus looks like. And you see that big thick blue line, imagine that snaking through your RV. That is what we call the bus. And then all those little gray boxes would be different devices, the generator, the inverter, lights, switch panels, touch screens, whatever else it might be. So this is what we call a bus topology. It's a little bit different than what you've often see in networking. A lot of networking like Ethernet is a point-to-point type system where everything runs to a hub or to a router. And then that hub or router or repeater then transmits the messages to where they're supposed to go on the network. This is very different. Being a bus, this means that there is no router, no hub, and every device is talking to every other device simultaneously. Every device can hear everything else. So it's like an old-fashioned party line, for those of you who are old enough to remember such things. That's an important point that comes in to this. It means that all our activity is very transparent and things can coordinate very easily without any kind of overhead, so to speak. Now, that does place some limitations on things. I'll explain in just a moment. That bus, imagine in a party line, if you have 20 people on a party line, one of the things that's important is that everyone talks at the same volume, right? It wouldn't do if you had one speaker shouting and others whispering. You'd never be able to get the communication. The whisperers wouldn't be able to hear. Shouters would obviously dominate the conversation. So CAN bus is set that all of those transceivers, they all operate within a very set, limited, I don't want to say volume, that's not technically correct, but set of parameters. And that bus has, as a result, there's some limits on that bus that are meant so that those parameters are right for everyone. So it starts with the material itself, that you can't use just any wiring. Your wiring has to have some specific characteristics. It's a twisted pair. That twisted pair also keeps out the noise, makes it so it both radiates less noise and is less subject to noise interference. But the characteristic of the wire itself has something that's called the characteristic impedance, which is essentially the, if you will, how well it transmits those signals. And it has to be a very specific amount. There also the volume, if you will, of the nodes as they're talking would be either too low or too high. So it does take a special kind of wire. It's not hard to find, but you do have to make sure you have the right stuff. It places a limit on the length of that wire. Since obviously if the signals are only at a specific volume, you can't extend them infinitely. But then the most important part is that at each end of that wire, you see those little red dots I placed? Those are called terminating resistors. And what they do is they absorb any the signal at the end of the wire, so it doesn't reflect back. There's no echoes. And you have to have one at each end, and you have to have no more than two. Because what they do, because they're absorbing echoes, that means they're absorbing the sound, if you will. It's not a sound, the signal coming in. And if you have more than two, that means your signal is going to be absorbed and more than it should. And now your volumes are too low and folks can't hear each other. The annoying thing about that is nodes that are right next to each other might still be able to hear each other. It's nodes that are, you know, widely separated or too near the extra resistor that can't hear each other. This is terrible in troubleshooting because most of your network will work, but as a whole, it doesn't. So this is one of the few truly cardinal sins. You must have terminators at each end of the bus and no more. Now, there's also a few little limitations on the drops. They can't be too long. They have to be reasonably close to the bus, and the total length of them is limited, again, so that volume is good and there's no ringing there. So there are some limits. They can't be more than 6 meters long, and the total of them can't be more than about 30 meters. So that means that your general strategy is to run that blue bus. If you're in a long coach, you might run it the length of the coach 2 or 3 times, maybe once in the floor and once in the ceiling, so that all of your drops are a relatively short length. And notice those drops, there's no branches on those drops. You have to go directly to the bus. So in some, the bus can be very long. It must be terminated, but never more than once, and never branched. Meanwhile, the drops have some limitations in length, but and they must never branch, and you never add any extra terminating resistors. So that's the topology in a nutshell. Now let's talk a little bit about the signals that are going to go on this topology. In the world of communication, there's 2 types of communication in general. That's what we call streaming, and then what we call packet-based communication. Now, again, for those of you of a certain age, I want you to think back to the joys of analog television. You know, we may have only got a couple different channels, but there was one thing that you know you got used to as with the old analog TV, and I will never get used to it with digital TV, and that is, in the old days when I was a kid, if I changed the channel changed. Now when I change the channel, now it sits and waits 1, 2, how many seconds, then the channel changes. Okay. Well, that's probably just barely tolerable for a television. It's not tolerable for a control network. So the fundamental reason for that is things like Netflix and cable TV, they're set for what we call streaming, the word. And in streaming, it's great for sending lots of data in a continuous stream. But then when you want to change the stream, it takes a little time to recalibrate. Let's see what that looks like in the next slide here. And here I show at the top of the screen something what a stream looks like on an oscilloscope. Look at those lines up, those vertical lines. Those represent data, bits of data, ones and zeros, and boy, it just goes on in this uninterrupted stream. And boy, it can sure churn out a lot of data. Well, what we do with RVC and CAN bus is something different. It's called a packet. And what you see at the bottom of the screen is some packet-oriented data. And you'll notice here, there's all the data is broken up into little chunks. There's less data. Now it's scaled there. If you were to scale the first diagram and the second diagram the same, you'd find that these little packets are just a tiny sliver of what you see in that stream. So little slivers of data, and separated. So what that allows is every different device to send its packets out. There's plenty of opportunity as soon as it sees that whoever's currently transmitting is done, it can then jump in with its little packet, and when it's done, other transmitters will transmit their packets. So you could imagine, I've got a little color coding on there with different colored packets. You can imagine those packets coming from different transceivers, different devices on the network. Okay, very different than streaming. What that means is we can change channels. We have tiny little packets that take less than take a fraction of a millisecond to transmit, which means that if you have something to say, if you have a command to tell something to stop, you're going to put that command on the network. It will happen within 1 millisecond. How fast is a millisecond? That is the time it takes for an Indianapolis 500 racer at full speed to go 4 inches. So your message to stop will happen at least that fast. Okay, now there's downsides to packets. The upside, there's no switching, it responds very fast, but the downside is it can't move that much data. The bandwidth is small. Can it do television? Yes, we can do television, we can do video with RVC. If your TV set has a 1/4 inch diagonal measurement. Can we do audio? Yes. If your definition of audio is the equivalent of the speak and spell you played with when you were in kindergarten. It's not so good at video, it's not so good at audio, but it is great for control messages and diagnostic messages running around an RV. So,
hi, Martin. This is Kyle. We do have a question in the Q&A box. I just wanted to let you know if you're ready to answer that.
So the question comes, do I have a position on how CAN lines go into a connector? So taking off the main harness, so only 2 wires in a connector versus snaking CAN into a harness, so 4 pins are needed. Okay, so one of the nice things about CAN bus is it in itself, the CAN bus, it's a twisted pair. And that twisted pair, the twisting is important in this, in that the twisting both makes it so it's much less vulnerable to noise, and also it doesn't radiate noise as much. And so that means it's perfectly safe to run CAN in a harness with all your other power wires, grounds, etc., and they won't interfere. Even sensitive things like running next to video. I have personally never seen a CAN bus wire create any kind of video distortion. So you have the option to run it in your harnesses. Now, because it snakes around a bit, that isn't always the most convenient. Sometimes you want to run it independently, and CAN's completely flexible that way. You can pull it out of the harness. And this is a very common solution. You know, I told you those drops can only be so long, right? So what happens if you have one or two items on in your coach that are very distant from the rest of your wiring, maybe from your main harness? You know, most of our RVs will have a main harness running typically down the chassis rail, typically one through the roof. And sometimes you'll have something kind of on the other side of the RV that you need to get to. The solution for that is simply to pull your bus kind of a loop from that bus. So you run the CAN wires down your harness, then break out of the harness, run over to the other side, and then loop back into your harness. And so with that, you can actually, you know, there's no need for long drops. You can do it all using loops, and you can get, you know, really anything done you need to do. And we're agnostic. It all comes down to what's most convenient. You know, in small RVs, your CAN bus can be, you know, a foot long. It can sometimes be in a small trailer. We've done some things like horse trailer conversions, you know, where you're very small living space, where the whole CAN bus is, it really comes down to a foot long with some drops, then going to the different places around the living quarters. It's very flexible that way, and you're not locked into any particular way to do things.
We have another question there, Martin, in the chat box now from Wayne.
Okay. Okay, no equivalent of UDP. Yeah, okay, that's, boy, you're getting into the weeds on this. That's going to be an RVC 201. So what I'd like to do on that is we'll explain the packet handling here next, and I think that'll clarify what Wayne's question is. So let's go ahead and on to the next slide here. And there it is. There's a packet. Does that answer your question, Wayne? No? Okay, maybe I'll have a little bit more explanation. This is a typical CAN packet. This is actually one, you know, you're looking at the diagrams on the previous slide. You saw the little ups and downs in the oscilloscope, the trace there. Those all translates into ones and zeros. So here you go. This is an RVC packet. It's that simple. Oh, should we go look at the next slide? Yeah, okay. Maybe it's not quite that simple. There are a couple of questions here. Question number one is, all right, all these ones and zeros, what kind of data is in this? This is an RV. Are we talking about, is this a packet saying tank levels? Is it talking about generator status? Well, we'll have to figure that out. Who sent it? What particular device is it talking about? And then I guess the bottom line is, what does it mean? Well, this is what RVC is really about. Everything I've talked about so far is generic to CAN. This could be a generic CAN packet. What we're going to talk about now is RVC itself, which is essentially nothing more than an enormous dictionary that answers these questions. It tells us what kind of data is in the packet, who sent it, What particular device is it talking about, and what does it mean? This is the core of what RVC is. So let's take this one step at a time. The next item, next slide.
Martin, Wayne did have a follow-up. He said relative to priority of packets, QoS.
Okay. Yeah, you know, a little aside here. So for Wayne, I'm going to point out the first couple bits in that packet are for a process of both prioritization and what do I want to say here, collision detection. I don't want to get into the details here, but every CAN packet has a specific priority attached to it, so that higher priority items get onto the bus preferentially over lower priority items. And then every packet also has, and it's kind of done invisibly to the programmer, a collision detection and corruption detection. Those are all built into CAN. So as developers, we don't have to deal with it. The bottom line is Bosch created those safeguards when they created the protocol in the first place, the CAN bus protocol, and we just get to inherit all that goodness. So we don't need to worry. As programmers, we can, number one, take for granted that any packet that we receive in our nodes, we can take for granted it's a good packet, that it's not corrupted, that it's ready to go. And similarly, when we send a packet, we can take for granted that it will be sent in order the priority. Our highest priority packets will go first. So that's all handled for us, frankly, rather invisibly. Now, okay, so the first question is, what kind of data is in this packet? We have a word for that. The word is DGN, data group number. And simply enough, certain bits, the first, there's about 17 bit, or excuse me, 17 bits in this that are referred to the DGN. And I highlighted them there, the 111111101010101. Now, that's all binary. I don't want folks, the non-programmers, to get intimidated by this, but this is something you could enter into the calculator on your PC, and it can translate that into a number, and that number then you look up in our RVC protocol, and that is ATS AC status 1. So those bits tell us that this is about the AC power coming from a transfer switch. And there's a table at the back of the protocol that tells us that is ATS AC status 1. That's going to be section 6.1.3 in the RVC protocol. Boom, that's it. It's that simple. When you're sending a packet, you put this identifier in it. When you're receiving a packet, you use that identifier to know where in the protocol is the information on how to decode the rest of this. Next slide. Now, who sent it? Next few bits here is what we call the source address. And this source address is unique to each particular transmitter. So when you get on the network, every device on the network gets a unique source address. This is just kind of like, you know, your phone number or the address for your mail. And it's key that everything is unique and you have exactly one. Doesn't matter how many different functions you have. So you might have, for example, a inverter charger that it's both an inverter and a charger and a transfer switch all built in. So it's doing multiple things, but it'll always have one source address. That allows a technician to look at that message and know exactly where it's coming from physically on the bus. So when you first get on the network as a device, the first thing you do is get a source address. You can either have it statically set or dynamically set. Both are acceptable. But you must have a unique source address, and you stick to it in all of your transmissions. Next slide. Okay. Now here, so far everything we've done is kind of fairly standard for CAN bus, but when we get to this next item, this is quite unique to RVC, and it's called instancing. So the source address tells you what transmitter is transmitting this data, but that is not necessarily the same as what physical device from the user's point of view it is. So for example, you might have a good example would be the transfer switch that we're talking about. So transfer switch is a unique device, but it has multiple legs. It has typically 2 inputs and 1 output. And if it's a 50 amp transfer switch, each of those inputs and outputs has 2 legs. So those are physical things that we need to identify. So when we're talking about this transfer switch status, we need to know, are we talking about the input or the output? Are we talking about the primary input or the secondary input? Are we talking about leg 1 or leg 2? Those are all encapsulated in what we call the instance. So in this particular case, those bits translate into leg 1 of the output of the main transfer switch. This instancing is one of the most important points to or factors in designing an RVC network. You need to make sure as an installer that your instances all match up to the physical devices in the RV. Typical example, simple example is lighting. On the network, the lights simply have instances. They're instance 1, 2, 3, 4, 5 on up to maybe 250. But for the user, of course, or the technician, they refer to a specific light. That's the galley light. That's the living room light. That's the bathroom light. That's the awning light. There has to be a proper identification or assignment between the numeric instance and the actual physical device in the RV. This is a configuration process. It might be something that's done by the vendor before he ships the product. It might be something that is configured by the OEM as he builds the RV. In the case of an aftermarket installation, be something that perhaps the technician does when he installs it, or maybe it's part of the product itself that it has some sort of dip switch that you set, or maybe you run an app to set the instancing. But you must, all instance devices, which most devices are instance, have to have some kind of mechanism for making that association. All right, then finally, let's talk about the data. So next slide. Finally, here's the data itself. Let's see what it means. So that DGN told us that we're going to go to table 6.1.3b. And if I break out the RVC protocol and I turn to that page, it'll show me a table, and it'll tell me that the first 16 bits of that, that's the voltage. And then the next cluster is the current. And the next one after that's the ground currents. And then the last little bit's the breaker size. Now, again, not to get too technical here with the ones and zeros there, but you can enter that into your calculator, look up in the table, and it'll turn out that those binary values there turn out to be 120 volts, 20 amps AC, got a ground current of 0.1 amps. And then the last one, the breaker size, unknown. Now, this is a key thing. The RVC protocol has, well, it's up to almost 500 pages of these tables. along with other stuff. And so the RVC committee has tried to think up absolutely everything that would possibly be relevant to, in this case, a transfer switch. And sometimes that means that the committee has put in provisions for things that your product doesn't support. Not surprisingly, the transfer switch itself may or may not know whether it's on 30 amp or 50 amp service. So that breaker size, it simply doesn't know. When that situation happens, you simply fill in all ones into that field. That marker means I don't support this, or simply that data is not available at the moment. In either case, anything that's receiving that knows to just ignore that field. So a very important point, probably the most common programming mistake done by newcomers is that they fill in those things with 0. But there's a big difference between saying that I have 0 ground current and saying I don't know what the ground current is. So we don't use 0, we fill it all in with 1s to mean I don't know, or I'm not communicating that at this time. That's RVC in a nutshell. It really is a matter of a massive document with these tables that show how to parse these messages out. All of those tables are organized by what we call the DGN, like you saw, and that's it. It's really no more complicated than that. So the work of the committee is mostly a matter of building up those tables. So let's take a little pause here. We've gone through quite a bit here. Let's see if we have any questions or comments. Okay. So I'm asked, can we show some of the tables? I didn't make a slide for that, but one important point is at www.rv-c.com, we post the RVC protocol in its entirety. And one thing that the RVIA has been absolutely wonderful about is making that data available for free to the public, just to download. They don't even ask for a registration. You can just download it. And not only that, and I'll talk about this a little bit more in a bit, but also the current business of the committee is also on that same website. And so you can track what members are proposing for additions and changes to the protocol. It's all very public and all very free. So www.rvc.com. Question, has any OEM embraced this more than others? I will just say the answer is, of course. As with everything in this industry, we have some early adopters. And I'll leave it at that. There's their integration with OBD. So that's onboard diagnostics. So there's some slight differences when you start talking about OBD, OBD2, OBDC, and so it's not quite where, again, we're not trying to interoperate with OBD, but it is relatively straightforward to bridge that information onto an RVC network. And that's in fact done in the field. There are coaches out there that have that bridging built into them. And then question comes up, how are devices communicating with each other? Is there something like the destination address? So as I said before, every node can hear every other node. And in general, that's what we want. But sometimes you might have two nodes that have something, if you will, kind of, I'll say secret that they want to be able to send to each other. I'll discuss the specifics in a bit, but the short answer is there is a way within RVC to do that, for one node to send another node kind of a secret message. The primary reason for that is for configuration and diagnostics, for a technician using a service tool to be able to maybe put a product into a test mode or get some configuration information that is supported under RVC, and we'll explain how in a bit. Next is there a master DBC file available for use? The DBC files refer to a database for a specific set of tools. Nobody has created such a thing, and there are some subtleties with that instancing in RVC that make that a little bit difficult, which is why I don't think anyone's ever made just a DBC file for it. Question comes, as a supplier of appliances, what is the best way to test the product to ensure the BGN is coded correctly to launch will work properly when integrated into production with an entire system? Okay, we'll talk a little bit more about this in a bit. So one of the big challenges is, as a vendor, how do you ensure that your product is going to interoperate with everything else on the network? So we'll be talking about that in a few minutes. So I think I would like to go ahead. Well, actually, let me get myself back on track here. So question for you. What reasons do products have for ever talking? Why do they want to talk in the first place? I think, one of these things might be fairly straightforward. Maybe I have a control panel that wants to let the user turn on a light, so you want to be able to issue a command. But what other reasons do we have to talk? Right up to the top, reporting errors. Absolutely. If anything's kind of the killer app for RVC and multiplexing in general, it's the ability to do diagnostics, to report errors in a common way that can be brought to the attention of a technician or to the user or to other products. Obviously, it'd be very important for a controller to know that the thing it's controlling is broken. Centralized control of information needs status. So Gary Johnson hits the thing. I've sent the command to turn on a light. I'd like to see a status message back from that light to say, yes, I've been turned on. Whether the device is alive or not. And this is key. One thing that RVC requires is a heartbeat. Every product must, at least every 5 seconds, send at least a basic message saying, I am alive. Okay. Could report status. Okay. So I came up with 5 basic reasons. So here's the list I came up with. Number 1, identify yourself. What's on this network? Pity the poor technician that plugs into an RV. The very first thing he wants to know is, what is installed in this coach? Number 2, report a problem. Number 3, report what you're doing. Give that status information. Number 4, send a command. Tell something else what to do. And then number 5, because a technician demands it. And this is exactly what we're talking about a little bit earlier. The technician being able to do tests or get detailed, maybe reconfigure the product. Those are our 5 core reasons. So we call these things identification things. We have 2 basic identification messages. One is the diagnostic message, the DMRV, which besides telling him any problems, also says, what basic kind of product are you? Are you a generator, or are you an awning, or are you a lighting controller? So you immediately, every device on the network can easily tell what other sorts of things are on the network. And in particular, whether or not a generator is on the network, whether or not there's an inverter available on the network. That every device can find out immediately. Number 2 is diagnostic messages. Excuse me, I almost forgot. Also with the identification. In addition, the technician can send a message and get from every device what we call the product ID, which is a user technician readable description of the product. That is to say, who made it, what's the model, would be the serial number if appropriate, and in some cases a secondary serial number, because sometimes like the hardware and the software are 2 different devices, 2 different versions or 2 different serial numbers. So that's all in a product ID that a technician can read. So when a technician steps into an RV and plugs in whatever tool he's using, he can immediately get a census of everything that's on the network and the basics of who built it, what type of model, etc. So he knows, where to look for help. Number 2, the reporting problem, that diagnostic message, then, just like in OBD2, we have diagnostic codes. We call them SPNs. And it's very much the equivalent of what you're familiar with cars, the codes that you get with the scan tools. We have the same sort of scheme, the same sort of codes. It's just that instead of referring to the engines, now we're referring to every different item in the RV. So now our technician can read everything that's in the coach and whether it's having a problem and the information on what that problem is. The third type of messages we call a status message, and this represents probably 90% of all the packets on the network. In general, every device is constantly sending messages saying, whether it be the transfer switch saying I have so much amperage coming through, or the generator saying I'm running and I'm at 1800 RPMs. These status messages are constantly going on the network, and it represent the overwhelming majority of the messages. Next, there's the commands, and with every command comes a status message. Every element, every transaction is transactional. There is, if I send a command, the device that receives that command is obligated to come back with a status, either saying that it fulfilled the command, or if it can't fulfill the command, it gives what we call a NAC, a negative acknowledgement, so that when you send a command, you always get one of those 2 responses back. So we get that feedback. And then finally, that last one, when the technician demands it, again, I'll go through this in a little bit more detail, but these are the proprietary messages that we use in service tools to configure, to test. And this is really powerful. One thing that we like to implement in our products, and we encourage all vendors to do this, is to integrate into your RVC support the basic production testing, often for your own purposes, because it's very convenient for your own production people, but also for the OEMs, the builders, to be able to troubleshoot and test your unit as it's being installed in the RV, And then ultimately that becomes accessible to your service technicians out in the field. So any sorts of self-tests that you can put in or detailed technical information, get that, if you get that into your RVC implementation, it is a really powerful tool for your customers. Now, I'd like to start to talk about some deeper philosophy. So far, what we've been talking about kind of applies to any CAN protocol. And it's not, we've talked about kind of technical things that frankly come pretty easily to engineers, but there's some deeper philosophy that is essential to understand. It kind of goes beyond just the nuts and bolts of designing a protocol, but into the deeper things that make a protocol last. And, you know, these are things that I'm actually pretty proud of that we laid out 20 years ago as we started to work on RVC, these very fundamental principles. And it's because we did that 20 years later, we're still using it, and not just using it, but expanding upon it. These are not the sorts of things you read about in engineering textbooks. There's not a lot of YouTube videos explaining these things, but they are absolutely essential. And for all of you who either participating in the RVC committee meetings or observing, you'll hear us in the committee meetings refer to these again and again, and it's key for you to understand them. I'm going to start with a simple one. Every message stands on its own. So that packet that we saw, it's not that big a packet. It was, only went across the screen once. There's not a huge amount of bits in that, but we were able to, even as small as it was, notice we could parse it out completely. When we looked at that transfer switch message, we were able to, just looking at that one packet, understand that came from the transfer switch. It was a specific leg, the specific output of that transfer switch. It was unambiguous how to interpret that. If you were looking at that in a big, long data log, you wouldn't have to look anywhere else in the data log to understand what's the contents of that message. This is crucial, because what this means is that even very simple devices, they only have to look at one message at a time. They don't have to keep a record of all the context of everything else that's going on in the network in order to understand what it needs to know. So for example, if I have, say, I want my air conditioner to automatically track the status of the AC power coming in, and if that AC power goes below, say, 90 volts, I want to disable my compressor so I don't have any low voltage problems with low voltage. All I have to do is look for one particular packet, that automatic transfer switch packets that we saw there, look at it from a particular instance, that would be the output in whichever leg my air conditioner is on, and then I just need to look at in this case, the voltage off that, and that's it. That is just a couple lines of code, and it's going to be extremely reliable, because it's that packet that's never going to change. It never has to, I don't have to look to see, maybe the instancing has changed, maybe my addressing has changed, maybe something else has happened on the network that affects it. I don't have to worry about that. I just look for the one packet with the one format, and that's it. As a result, you can implement RVC with some absurdly small processors, very inexpensive, and this is key for reliability, because that code is so simple. the probability of a bug or a malfunction is extremely low. Now, there are some exceptions, and that is when it comes to diagnostics and configuration, things can get very complex. And so we'll talk about that again in a little bit. We do have some messages that are direct from one node to another, and there's some context then that comes into that. But in general, for our general operations, every message stands on its own. Okay. Now, almost a corollary to that is that all the activity can be fully understood just by looking at the packets. No activity is invisible. So that means a technician can look at a data log and fully understand how that data and all those packets translate to actual activity in the RV. So in this, we saw that with the transfer switcher. That's unambiguous that at that moment, the voltage was 120 volts and the amperage was what it was. Okay. That same principle applies to all the activity on the network. There are no ambiguities and there are no secrets. Okay. Again, exceptions for the diagnostic / configuration. But the key here is that this eliminates the finger pointing. One thing that's essential to understand is RVC was designed from ground up to be massively multi-vendor. Parts coming from many different vendors and the builder then assembling them into a unified system. It is essential in that at the end of the day that the builder can understand everything that's going on in his RV. And if there's any unusual activity, and this is, of course, things can happen here in terms of misconfiguration and the like, but if I press a button here and I get an unusual response here, I expected that button press to turn on this light, but instead it caused the awning to come out. We can go to the data log and understand unambiguously what happened in that transaction. You can see the actual message from the button press from the control panel and see and interpret exactly what that message is supposed to mean, and then look at the response from the other products and see whether or not they understood the message correctly and how they responded. So it is perfectly understandable, and there's no ambiguity, and there's therefore the finger pointing ends. Now, corollary to that is we can't have any sort of secret messages, little tricks, special filters. It is tempting to want to put in, say, a password into your product. Now, and I've heard a lot of different explanations for why why vendors feel this is necessary, but this is very much against the purpose of the protocol, the spirit of the protocol. RVC is all about safety, and we have safety interlocks built in as part of the protocol. We have explicit ways of communicating whether or not the park brake is set and whether or not the ignition is on or off, or whether the vehicle is in motion. These things are explicit in the protocol. And you can implement and are expected to implement all the essential safety features that come with that. But crippling your product by putting secret things into it, that means the OEM can no longer be able to vouch for what's in his product. Ultimately, it is, after all, the builder, the OEM, that is putting this product on the road. If there's a safety issue, NHTSA is going to the OEM, not the vendor, for satisfaction. And so it's essential that that be in the that the OEM can observe and control that interaction. So this is one of the probably least understood but most important aspects of RVC. Next, again, a little bit subtle, but we've talked about this a little bit physically. We have to understand there is no master, but there may be many users. So we talked about this a little bit on the data bus, that every node can talk to every other node. There is every node is meant to be self-contained in the sense that it, for example, if you are a generator, you receive generator commands, but whether or not you start or not is up to your own logic. You may have, for example, interlocks which say, I don't start the generator unless the generator slide room is closed, for example. That logic is meant to be internal to the generator. Similarly, if you're a slide room and you want to make sure that you do not move unless the park brake is engaged and the levelers are set, you implement that logic in the slide room, not at the user interface, not at the control panel. But whatever device is receiving the slide command is the device that is then looking at the park brake status and the leveler status, deciding whether or not it should actually move. If it can't move, then it sends a negative acknowledgement and says, nope, physical conditions do not allow this. But if you receive the command, you're going to give one of those two responses. You're not looking to something else to make the decision for you. And this is crucial. This is because there may be many users. There is, when you talk about a control panel, there is not just one control panel. A typical RVC system, there may be more than one touchscreen. There may be switch panels. There may be a tablet interface. There may be a cloud connection. There may be voice control. There may be all kinds of different methods of control. There may be many users. Oftentimes your devices might be commanded by other devices. For example, the inverter charger might be commanded by a battery controller to change its settings. So you have to be built in that idea there may be many users. So it's important that, first of all, as designers, we design that autonomy with that in mind. This is also one of the tricks I really see people that don't have experience in multiplexing trip up here. But we're kind of used to in our own labs that it's our control panel and our device, and there's one control panel and one device, it's one-to-one, and we don't have to worry about all of this. But that's just not the way a modern multiplexing network works. And we keep this in mind as we design the protocol. And the corollary to that, go ahead and go to the next slide here, is that every device, excuse me. Lost track where I was on my my notes. Next is that every device identifies itself fully. Okay, and you're not allowed to lurk, and you identify yourself not just that you're on the network. It's what kinds of functions that you have, their make and model, and also your activity. No invisible activity is allowed. Even if, for example, suppose I have an awning, and on the awning itself there is built in a switch, sort of a manual switch to override the RVC activity. When there's activity on that switch, you still broadcast your status as though that was RVC activity, so that all the activity is there and you are fully identifying what you're doing at all times. Now, the last one is one of the trickiest and most subtle. This is something that we've seen other industry associations kind of trip over, and I think we've done a really good job of this. As committee members and as an RVIA, we have to understand that we're just providing a dictionary, we're providing a language. In the course of that, we have to make sure that the language we're describing here doesn't ever dictate the product design. And I'll give you an example of what I mean. Consider the thermostat and the air conditioner. You could have a smart thermostat and a dumb air conditioner. Air conditioner you could treat as it's just a compressor and a fan, and it could just be receiving air conditioner commands to turn on the compressor and put the fan speed to 50%. Be a very dumb thing. It doesn't make any decisions. It just listens to commands and sets the compressor and the fan accordingly. And it might be mated to a smart thermostat that is actually looking at the temperatures and deciding, all right, it's time to turn on the air conditioner. Now it's time to turn off the air conditioner. Okay. But that's not the only way you could set up a system. You could set up a system where it's a smart air conditioner and a dumb thermostat, where all the thermostat does is say, well, the user set me to 70 degrees and cool mode. And the air conditioner just looks at that thermostat for that information, but it makes the decision, well, I'm going to run my compressor now at such and such a fan speed, and all the logic is there. Those are both completely legitimate ways to build an air conditioning system. And it's important as a committee that our protocols support both of those techniques. Not only both of those techniques, but other techniques as well. You could integrate all that into one controller. It could be, there's several ways you could do that. And it's key. Our protocol should never dictate the design of the product itself. It only dictates how the products communicate, but not how that gets embodied into the actual hardware, as it were. So this can be a little tricky for the committee, but it's very essential that we maintain this. The way we do this is through the RVC committee. And this was also one of the things that we established very early on. If we're going to be successful as a protocol and as a committee, we have to make sure that, number one, we're very responsive. In this industry, product development happens fast. And we have to have a committee that can respond to that. We look at other industry associations. The SAE actually is much better now, but for a long time, it took years, sometimes over a year, I should say, for business to be transacted. The Bluetooth organizations are kind of infamously slow. We set up a system in which that if you, as a vendor or builder, have a proposal for an addition to the dictionary, as it were, to the protocol, or any kind of concern or change, that gets posted, and you should have a response in 30 days. It'll either be approved or not, and you'll have obviously a chance to update it. That system is done in public, and it's consensus based. The way it works is simple. You go to on rvc.com. There's a spot there called official business. You send an email to the administrator. He posts it on that spot there. He sends out an email to the entire RVC committee indicating that there's some activity. There's a proposal on the website, and everyone has 30 days to respond. If there are no objections after 30 days, it's automatically approved. If there's any objection, then it's automatically not approved. And of course, in practice, almost always those objections are of a technical nature, that it's a matter of getting worked out. And if you look at rvc.com, you can see some examples in the archive of where engineers have gone back and forth until they've got it dialed in and the result was approved. But the bottom line is, that you will be within 30 days, you'll have your answer. And almost always that answer is going to be yes. Sometimes it's yes with these suggestions and improvements. The system has worked extremely well. In the 20 years to date, I believe we've had exactly one proposal end up being abandoned and not approved in the whole process. And because it is consensus based, we do require 100% approval at that. Everything's high quality. Not a lot of mistakes get through. Generally, once we've approved something, it kind of gets approved once. We're not going back to it and making revisions because we got it right the first time. There is the business of the committee itself, which does meet something on the order about twice a year. And that works like any other RVIA committee. It is an opportunity there to deal with more controversial items. But honestly, most of the business of the committee there is the kind of the long-term issues like education, policy things, where the issues coming up probably at the next RVC meeting will be, what do we do for, say, Bluetooth supports and things like that that are at a higher level. Most of the day-to-day stuff that we deal with as engineers happens on the RVC.com forum. It happens very fast, very open, and very effectively.
Martin, we got a question on the Q&A box there.
Okay. All right. So question comes up. It has been a while, but the last I looked, the RVC protocol requires a 1-second heartbeat message. And so that makes it hard to do sleep current. So has that changed? It has changed. The current heartbeat requirement is 5 seconds. And we have not specifically addressed the issue of being able to completely go to sleep. That really hasn't come up in discussion. Kind of the assumption is that these are all wired products and therefore have DC power available to them. And so we haven't worried too much on the power consumption. If that is a particular interest, that is the sort of thing that would go onto the RVC.com committee as a proposal. And you would very quickly get some input and perhaps even a necessary changes to the protocol. Okay. All right. Now, you might have noticed at this point that I usually say the words protocol or standardized protocol. Yeah, I don't think you've heard me just say the word standard all by itself. And that's because the RVIA calls this a recommended practice, meaning that the RVIA recommends that if you want to do multiplexing, you do it this way. But we don't call it a standard because we're not a standards body. The moment we say it's a standard, that opens up all kinds of legal liability type issues that the RVIA is not in a position to deal with. And it also opens up issues with testing and such that the RVIA is simply not equipped to become a testing body. So the way we like to put it, we're not the cop. We're just the guys making the little yellow sign before Dead Man's Curve. And if you want to go more than 35 miles an hour around that curve, that's on you. That's your engineering decision, and we're don't recommend it. Now, there's a little bit of confusion that sometimes pops up. When we say it's a recommended practice, we mean the entire protocol is a recommended practice. It's important you understand that you can't just pick and choose what parts you want to follow. Not because RVA is going to take the sticker off your RV, but because every rule we have interacts with other rules. Making up your own DGNs or modifying the formats of DGNs is just a recipe for disaster, because someday your made up DGNs are going to collide with somebody else's who made up their own DGNs, or your changed packets going to interfere with someone else's changed packets. Some of these things are the laws of physics. What I talked about, the wiring and making sure you have the termination, those are physical laws. The RVA industry recommends you follow those practices, but that's one that's kind of like, we also recommend that you don't exceed the speed of light. These are not good ideas. Some of the other things, if you break the rule, it'll disrupt the packet transmission, sometimes in unpredictable ways. This is kind of essential to understand that just because the RV leaves the factory looking like it works doesn't really mean it works. If you've broken the rules, you might not realize it, the ramifications of it, until well after the fact. If you stick with the rules, then your systems will work. If you break the rules, not only do you run the risk of failure, but that failure may not be detected until the RVs are out in the field and creating problems. So it's a recommended practice, and when we say that, we recommend all of the practice. Okay, now I promised you a little bit of talk about proprietary messages. So if we go to the next slide, this is it in a nutshell. Yes, you can have secrets. However, there's limitations around those secrets. We said before that what's essential is that all the activity on the RV be transparent, so that the coach builder can understand everything that's going on in his own RV. And heaven forbid if NHTSA comes calling or anything like that, any regulatory body peeks in, they can actually show what's going on in their networks, understand it, and therefore be able to take responsibility for it. However, there are cases in which you have legitimate, and if you will, secrets. These tend to be the deep things within our products. Typically, there are things like configuration items, the things like tests, protocols, and to do that, we have what are called proprietary messages. And these are messages which, in the DGN, in that first part of the packet, is embedded a specific destination address, and only products with that the product at that address is to listen to it. All other products are to ignore it. If they listen to it, it's at their own risk. And what that allows, and within that message, then the body of that message, as a vendor, you can do anything you want. And if you wish, you can encode it, encrypt it. You can put whatever sorts of schemes you like. It's completely up to you. What this does, it means then we have a common method of handling those secrets, so that technicians and their service tools and so on, there's no interactions that you have to worry about. You don't have to worry about your service tool interacting with settings from somebody else's service tool. It's all clean that way. and you can do, go ahead and support whatever fancy technology that you have. The question comes up, if you have a new product, the question comes up that you often want to kind of keep it under the cover that you have something new until the last minute, so as to gain whatever competitive advantage you can from it. Let me just give you a couple of rules of thumb. And first of all, understand that's one of the key reasons why we made the committee business work so fast. You can, as a developer, you can wait until 30 days before, public launch, before you have to submit that to your new information to the committee to be added to the protocol. So that takes you, right up to the edge. You're typically you're prototyping in RVs at that point. So you're very late in the process typically. But the question comes, what belongs, at what point do you need to add your new feature to the protocol? So typical example, suppose I have a, let's see here, we'll take an ice maker, and I have a new debubbling feature in my ice maker that will cause the ice to be created more slowly, and therefore will have fewer bubbles in the ice, and it'll be better tasting ice. That's my brilliant design that I have now a choice between fast mode and good mode. All right. Question is, do I put that, is that required to be in the RVC protocol? Or can I do that entirely under the covers as a proprietary message? And the simple rule of thumb is, if this is something that as a user, it would be in a control panel, you would have a light on the light or a button on the product itself, perhaps, that would indicate that. If there's anything that would be, especially if it's necessary, but even if it's useful or an advantage to have for the user, then it belongs in the RVC protocol. If it, on the other hand, if it's purely at a technical level, that it's only for technicians, or it's only at the installation level, then it does not need to be in the protocol, and you can just do it for the proprietary messages. So of course, if it's user-oriented information, then it's not really terribly secret, obviously. And so that's I think a fair rule of thumb for you to decide whether or not to make a submission or handle it this other way. Are there any questions on that? Okay. All right then. So, so far we've talked about really things that we set up 20 years ago. Everything I've said so far, I could have given this seminar in 2005 and it would be exactly the same seminar. But it's not 2005, it's now 2020. So let's talk a little bit about the present day and in the future here. And really what I want to talk about is how is this impacting our industry? Let's start with the technicians. What are we doing today? What about RVC is going to impact the technicians? And how's that going to work in our industry here? And I'm going to start off the discussion here with two words: sonic screwdriver. All the Doctor Who fans out there know that the sonic screwdriver is this wonderful little prop that Doctor Who has that lets him fix just absolutely everything. And that is exactly what RVC intends to be. The one thing I didn't mention earlier, but every RVC network is required to have a little diagnostic port, little 9-pin connector that is standardized and is intended to allow the technician to plug in his service tool, typically a laptop, could be something else, into that network and draw out all of this diagnostic information and have tools to configure and test everything on the network. But what that means for technicians, to start with, it means he's got one way of doing things. He only has to have one set of tools, and he only has to train, well, he still has to train on the individual products, but the basic, that training can start with already the assumption that he understands how to get into the network. So as vendors, we get to build off of each other's work, infrastructure, so to speak. And as builders, we have a program for training that is both more universal, faster, easier to learn, and also builds off what every other OEM is doing. So our training requirements dramatically reduced. We've had talks. I'm surprised we haven't seen this yet in the industry, but you have to understand what has happened in the automotive industry. Those of us of a certain age might remember that in our youth, automobile dealerships hated service. Their service department was out back. It would be the minimum required to keep their franchise agreement active. If Ford said they had to have 3 service bays, they'd have 3 service bays, never more. Today, the service in the automobile dealerships is front and center. It's not an exaggeration to say that these days they sell the cars to get the service business, because service is now very profitable for them. And why is it profitable? Overwhelmingly, it's because of the electronics. Now, the technician can plug in his service tool into the car and very quickly get to what the problem is, get the solution, get it right the first time, process the paperwork, and all that in a fraction of the time, and services become profitable. We have the potential with RVC to do exactly the same thing. And I'm anxious to see that grow. Probably nothing excites me more in this industry than see that growth in the technicians' capabilities. Next up, let's look at the engineers. They're at the OEM level. And this is a key, and here again, 2 words: electronically interchangeable. I say electronically interchangeable. Goodness gracious, right now in this COVID era, we're having, I'm told, just a few slight supply problems on a few components here and there. And boy, wouldn't it be nice if I've got a shortage of this brand of, say, awning, wouldn't it be nice if I can just interchange a different brand of awning and get it out the door? Now, physically, we've always had to deal with the challenges that they all mount differently, et cetera. And we can't do anything about that with RVC, but at least we can make the control systems interchangeable so that we're not having to making massive changes in the programming of our system. And this is right now the biggest area of work of the RVC committee. The RVC committee has set up task forces and is developing tests and documentation to enable vendors to make their products interchangeable to within whatever set of features the OEM is looking for. Now, it's not a requirement that every product be the same. It is simply saying that if your product is going to support a particular set of features, that it supports it very specifically, these messages, and sometimes some parameters like timing can be required. So it's just to remove all the ambiguity that can come up. So for example, we talked about earlier the thermostat and air conditioner, and how we can have smart thermostats and dumb air conditioners and vice versa. One of these task forces has done is explicitly stated that if you are a dumb air conditioner, you will at least handle these particular messages in this particular way. And there are little subtleties that have to be worked out in that. For example, what do you do with fan speeds if you're only you only have a fast and a slow 2-stage fan but you get a command that might have been intended for a 3-stage fan. There are these little ambiguities that exist in any kind of protocol that the task force has been making explicit, and therefore making it much easier for builders to switch products back and forth. There's similar profiles then for a smart air conditioner. And similarly for the thermostat, there's profiles for a dumb thermostat and a smart thermostat. And then within those profiles, there are additional profiles for things like how they handle power management. And this is really kind of where a lot of the work is being done today, is moving past just being able to turn things on and off, but making things more manageable and automated. Things like the power management being directly handled by the software through RVC, so that if you, for example, don't have enough amperage to go around for all the air conditioning and the other appliances in the RV, that it all automatically turns on and off appliances in a predictable and effective manner. This task force has outlined 3 levels of compatibility. So next slide. So the first level is really simple. Level 1 is it won't break the network. That's sort of the lowest bar to clear, the most essential, obviously. That's been defined by our task force and is being turned into explicit tests. Level 2 is making sure that your products obey all the fundamentals of RVC, all those things we talked about earlier in terms of that it handles commands from multiple sources, that every message that it sends stands alone, that all of its activity is transparent, that it sends all of the identification information as desired. So that's what we call the level 2 compatibility. And then level 3 compatibility is the ability to directly substitute for other products of the same type. And that level 1 and level 2, the same set of rules applies to every different kind of product. The level 3, each different type of product has its own set of tests. And so that has been a massive amount of work being done by these task forces, and still ongoing. The latest draft of it brings us our protocol now to, I believe, 493 pages. A very substantial amount of work, and still ongoing.
Martin, we have a question from Roland in the Q&A box.
Okay, so question, for a multiple instance device, do all the instances share the same address? Okay, and or identify the instance byte, the message data. So here's a key point, going way back to that, the interpreting the DGN. The difference between the source address and the instance, they're completely unrelated. That is to say, the source address identifies what physical transceiver or CAN controller microprocessor is sending the message. But that may or may not have much correlation between what the instance is, which is what physical device in the RV. So for example, I might have a lighting controller, or I have one lighting controller controlling 8 lighting instances. So all the messages would have the same source address, but they would have 8 different instances. Now, it might be that I have 2 lighting controllers, each with 4. And so in which case, all the, all the instances, the first 4 instances would all be being sent with the source address from the first controller. The next 4 instances would all be being sent from the other controller. So there is no particular correlation between the two. The source address it's the location of the microprocessor on the data bus. The instance is the location in the coach itself of the device. Some examples of instances, by the way, like the fresh tank is a specific instance. The gray waste and black waste are all specific instances of a tank. We saw how in the transfer switch that we had instances being the legs and the inputs and outputs of the transfer switch, but then the transfer switch itself has its own instance and that's built into that, because you can have a coach with more than one transfer switch. Instancing can get a little bit complicated. We try to simplify things. A lot of the instancing is defined like we did with the tanks, where a specific instance has a specific meaning. And other things, for example, in the case of the air conditioning, we say that instance 1 should be the most forward and typically the main zone in an RV. Sometimes that's ambiguous. In a fifth wheel, it'd be the other way around. Typically, it's the most backward, rearward compartment. But zone 1 is typically the main living compartment, and then it goes 2, 3, 4, as you move back through the RV. But they are very separate things. The next question says, will the RVC specification be updated every time a new proposal gets approved? Okay, so as a practical matter, the committee, it's almost 500-page document. The administrator can't update that and release that with every specific change that the committee that happens on rvc.com. That's why all the business on rvc.com stays on rvc.com. And you can always go back and look at the current business. And there, at any given time, there might be a month or two, or maybe a couple of months worth of business on the website that hasn't yet made it into the main document. So you do have to look at rvc.com to make sure that you're completely up to date. But as a practical matter, it's 500 pages. He just can't release that just on a week-to-week kind of basis. Okay, next up, let's talk about the vendor's point of view. We've got the advantage now for the builder. He can start mix and matching product a whole lot easier, and it can be fully confident in the system that he builds, in its safety and its functionality. Now the vendor's point of view. The key thing here again, 2 words: stable target. RVC, and especially this work that the committee is doing right now in creating these specific tests, this gives the vendor a stable target to develop towards. They only have to develop things once, and it'll serve the entire industry. And it's an infrastructure that's been around now for almost 20 years. So it's going to be around for I think a long time in the future. And so that enables the vendors to invest their engineering resources knowing that they're going to have an appropriate payback for it. I strongly encourage all vendors to participate, at least keep an eye on rvc.com, work with these task groups in your areas of interest. It's extremely important, and it's a great service to the industry. This is your opportunity, and we don't get to do that very often as vendors, where we actually get to help write our own rules. And this is one of those opportunities, and I certainly encourage everyone to take advantage of that. And then finally, of course, this is all worthless unless it works for the customer, the end user. And, in 2 words, stuff breaks. And what RVC provides for the user is, number one, the assurance that when stuff does break, that they have some means of identifying it, they have some hope of being able to get it fixed, or, even if they can't fix it themselves, they at least have some sense of how much they're going to pay. And also that down the road, their RV does not become obsolete. This is a key thing. Maybe I didn't give enough on this earlier. Most electronics in this world they're consumer electronics, and they are designed and built with the idea that they're going to be thrown away and made obsolete in 2, 3, 5 years. RVs are not consumer electronics. RVs are consumer durables, and RVs have lifetimes of 20 years and more. And RVC gives them the hope that the RV that they buy today, the 10 years, 20 years down the road, as things break, they'll be able to replace them. Not that, of course, specific products may be obsolete by then. They might not be able to get that model of inverter or water pump or what have you. But there will be RVC inverters and water pumps and such available. And it won't necessarily be plug and play. That's not realistic with the complexity of the products that we have and the depth of the interactions. But at least there'll be plug, configure, and play, that you can plug in the new product and the technician can make whatever adjustments in the configuration to make it interoperate properly with the older products. That is such an important promise, absolutely essential in an industry in which we have so many things in our RVs that are built on a consumer electronic basis with short lifespans. But the reality is these RVs last for years, often the most important purchase that customer ever makes. And RVC gives us the chance, a promise to them that they're not going to be left high and dry. So, all right, we're down to just about, it looks like about 5 minutes left. So, last opportunity for questions, for comments. Anything left that you think I should go over real quick? Oh, I'm watching the participant number dwindle. Okay. Do we support BAM messages? Okay. Nick01 is clearly a design engineer hard at work. So BAM messages refers to long messages. I showed you those packets. They only showed a limited amount of data. And there are times when we need to do longer messages. For example, that product ID. And for that, there's a protocol called BAM. And yes, it is supported under RVC. We actually use the simplest form of it. We don't like using it. We use it very sparingly for things like product identification. but it is supported and used in there. I see a question about any Bluetooth RVC thoughts. There's lots of thoughts. There's almost, that's one of the things on the horizon. It'll almost certainly be a topic at the next RVIA or RVC committee meeting in person. So there's a lot of ideas on that, far more than I'm going to come up with, talk about in the next 3 minutes. Mike says there's a number of devices limitation on the bus. There is, but it's a pretty large number. It's on the order of over 100 nodes. I've never seen a bus come close to that. Next, CAN tools, Omniscope, the only field tool available. Not going to talk too much about that because it's in my self-interest. Omniscope is a product of my own company. To my knowledge, we have no meaningful competition. I'll leave it at that. Is there a recommendation who can check RVC compliance for newbies? I'll follow this up with your first thing, a little bit self-serving here, but Omniscope does give you a quick way to see if you've got the basics of compatibility. That's the first place I would start in any project. Let's see. The question comes up, what about CAN FD? CAN FD is a new technology which is gaining some traction in some other industries. It is essentially a way of packing more bits into the same time frame, that same packet, as conventional CAN bus. Frankly, there hasn't been any particular interest in that. Right now, RVC networks are not so heavily loaded that we've been too worried about having to pack more packets in. And CAN FD doesn't really solve the fundamental question. It gets more data per packet, but most of the data that we're sending, we're not even filling the packets that we have. So it doesn't really have a huge benefit for us. So there hasn't been a whole lot of work in CAN FD. I see some thanks and I appreciate. And okay, for the previous question, let's say an RV has 3 solar controllers installed, each of them will each of them have a unique SA and unique instance? Okay, so my 3 solar controllers, without getting in too deep into the details, you'll almost certainly have, since each of those solar controllers themselves would have a microprocessor and a CAN transceiver, you would have 3 source addresses and 3 instances. Those would each have their own drop off the data bus. Another way to look at it, every drop on the data bus gets a source address. And then every physical installation gets an instance. So here you have 3 drops from the data bus and 3 physical sets of solar panels. So three addresses, 3 instances. Okay, thoughts of brides to, okay, NEMA 2000. So the big hurdle with NEMA 2000 is the NMEA uses NEMA 2000 as a way to raise money. That's part of how that association works. And that puts a big crimp on our ability to cooperate with them because everything we do is open, wide open. And so it's very difficult for us to work with the SAE and the NMEA 2000 directly because of that. Now going back to the RVC protocol being recommended and not a standard, is there a way for manufacturer to verify that a vendor's product is following the rules without actually installing it? And yes, this is, as I say, the hottest topic in the committee. This is what the working groups are working towards. And I encourage especially the OEM engineers to get involved in those working groups if they're not already. So those tests are literally being created as we speak by these task forces.
Thank you, Martin. I think there might be some in the chat box there. Did we get the last ones there? Did you answer the one by Lars?
Okay, so file download for. Okay, so Lars has a question about doing file downloads. Actually, RVC has a download protocol already supported, and several companies are using it. We've been using it at Silverleaf for about 16 years. So that protocol is it's pretty wide open. It works pretty well on a variety of products. So we use it for some very small products and some very large ones. So the answer is yes, Lars. And if you have any questions on that, why don't you contact me offline and I'll be happy to go over that with you. I believe in answer to Bill's question, I believe this whole webinar is going to be published, Kyle.
Yes, it will.
Yes. And then I think the slide deck would be part of attached to the video some way.
We can send that. We can distribute that after the webinar. Yes.
Okay. Okay.
Great. Thank you, Martin. This has been very educational. I think we've all learned a lot. I know I have. If anyone on the call still has questions related to the RVC subcommittee, how to get more involved, you can contact me. I'm going to put my email address here in the chat box. You can send